Okay, a quick transition, but it's the same thing. Huzzah. Yes. Yes, I'm using this document camera to look at my surface. Yes, all of the other instructors are actively laughing at me about this, but hey, we do what we can with technology. Okay, so we need to fill in this array to represent this disjoint set. This is the way you're going to be implementing it for Project 4. So let's perhaps start with hopefully something that asks a little bit less of us. Let's try and fill in the very first space right here, index 0. So at index 0, I want to store the representative parent for the node with the data 0 stored within it. Which set is the 0 in? 0 set. Yeah, it's like, boom, just this set hanging out by itself. You can imagine that maybe what happened is we called make set on the value 0, and then it hasn't been union together yet. Still waiting for its family. So what am I going to store here in this element space? Anyone? Anyone want to raise their hand, give it to us? Yeah, please. -1. I absolutely agree, because the weight of the tree that this is the overall root for has a weight of 1 itself. So I'm literally just going to store the value -1 there. Yeah? Okay. Let's do another one. Let's see. How about this node down here? So it is the node 18. So I'm going to fill in this index of the array. And what am I going to store as its parent? 17, absolutely. So I'm going to put a 17 in here, and that means 17 is my parent. Now let's kind of work our way up. What am I going to store in 17's spot? I heard it. Yes, 15, exactly. I'm just looking at it. There's my 15. Okay, and what am I going to store in 15's spot? 11. I love it. So we're going to put 11 there. Great. Now, what are we going to store in 11's spot? Ooh, I love that. Okay, I heard a universal negative. Interesting sentence. But yes, anytime we are writing down the parent of an overall root, i.e. that person doesn't have a parent, that node doesn't have a parent, it's going to be a negative number. Initially, we were like, just make them -1s, then we know. But then we were like, woohoo, maybe we can be clever and we can store some information there. And so we stored -1 here because this has a weight of 1. Here, we're going to store -8 for those people that had that one, because that will then represent that overall tree has 8 items in it. So I'm going to store -8 right here. Any questions on that piece? Love it. Okay, let's maybe do one more little journey here. Let's do, what about this node? Which index of the array am I going to update to store this one's information? Where in the array am I going to put this person's parent information? 8. I agree. Just direct mapping. Okay, now, what am I going to store in this box? 7. I love it. Okay, then what am I going to store in 7's box? Yeah, exactly. And then what am I going to store in 6's box? 1. All right, and then we're finally up here, and this is the pull everywhere question. What am I going to store in 1's box? -10. There we go. Yes. Question. Yes. Yes. I was just giving you some examples, but yes, you would need to fill in every spot. So for 16, what would I put there? 15, exactly. There we go. Yeah. Yes, question. What is the integer ID of each node? Is that what your question was? Of each step? Oh, each set. Oh, sorry. Yes, great question. So there's sort of, we were doing these things called like representatives, right? And I would say in this case, we'll just make the representative 0 because that's the overall root. And maybe here the rep is 1 because that's the overall root. And maybe here the rep is 11 because that's that overall root. That's probably what I would do there. Any other questions? Yes? The question was, did I have to do this like direct mapping kind of thing? And the answer is no, I didn't. I just picked it because it was hopefully a little easier for our brains. But chances are that you're going to have int values that also make sense in your array indices is pretty low, right? Like chances are you're not storing the numbers 0 through 18 kind of thing. Chances are you have names like we saw in the previous examples, or maybe they're student numbers or something like that. And if you had that case, then you would want that sort of like quick find map where you have your like key values, and maybe that's like, you know, your like data. And then you have your indices. And that would be your value. And so that would be something like, oh, like if I want to store Casey in this disjoint set, well, then maybe I like add her to my little map. And if Casey's the first person, maybe she gets to claim the 0th index of the array. But it is technically totally arbitrary. It's totally up to you as to which index of the array stores which parent. Usually the way that I would approach this is when you are creating a new node and adding it into your disjoint set. Just add another item into your map and just sort of take over the next available array index. So it's almost like, you know, like the first thing added into your disjoint set, its array index is 0. The last thing added into your set is array index size -1 or whatever you want to call it, something like that. Great questions. Any other questions? Cool. Then hang on. Okay. Here's some of the, there we go. Yep, there's some of the answers of it. Oh yeah, this is a fun little one. Technically, ints only take 4 bytes of memory. The operating system specifically optimizes for them. So not only do we get like constant time lookup and put and things like that because we're using an array, we are actually using less space in the computer to store just these ints in an array than if we were to store an object with an int field with another like, you know, parent field, et cetera, et cetera. So we've really, like, this array representation is super optimal, not only from a runtime perspective, but also from a memory usage perspective. You still have to know the trees. The trees are still real? The trees still exist. This is just a representation of the trees. Let's do it again. Yay. Okay. This is me trying to help us out. And so, you know, we've got our first checkpoint coming up. Go ahead and do this again. Fill out this array for these items, and then we will chat about it. Go ahead and take 2 minutes. Feel free to chat amongst yourselves. All right, we're going to transition again to... Okay. All right. This is the same picture. Okay. Let's see what we've got here. How How about let's just start at the beginning again. For index 0, what am I going to store in this box right here? Ooh. So this is my node 0. And so I want to represent 0's parent. I heard somebody say it, so I'm going to put a 3 in there. Maybe jumping over to 3 then, what am I going to store in the 3 box? -6. I absolutely agree. Sorry. Oh, God. Okay, I'm going to ignore that text message. Okay, now, let's see. What else do we want to do? How about 5? What am I going to store at index 5? -1, I agree, because it's an overall root. It's got a weight of 1. Sounds good. How about, let's pick one over here. How about like 14? What am I storing 14? 12. I like it. We're getting some speed here. Okay, what are we going to store in 12's box? 13. Cool. What are we going to store in 13's box? -8. I love it. Okay, perfect. There we go. Does anybody have any questions? Now we've done this twice. Now, let's do the union call, and we're going to include our optimizations. So for our union call, we are going to union 2 entire sets together, and we are going to make sure that the larger tree, the heavier tree by weight, absorbs the smaller tree by weight. Also, we're going to path compress as we do this. So we're going to make a call on union of 2 and 16. So the very first thing I do whenever I call a union is I technically call find set of each item. So I'm going to call find set of 2, and I can see that 2 is right here. And I know I didn't fill in our entire tree, but then I realized looking at that 2's original parent should be 0. I think I filled in 0, and then I think I filled in 3. So by doing this find set, I would realize that 2 exists in the set whose overall parent is 3. But as I went on that journey, I realized that I can point 2 directly to 3, and I can point, 0 directly to 3, even though it technically already points there. But if there was anybody else like along this path, I could have realized, hey, they all, eventually point up to 3. I'm going to add them to my little list of things to path compress. But so right now, I'll kind of keep that list like that. Let's call find set on 16. So I would jump into this index of the array. That's what I would do when I am calling find set. And I didn't fill it out, but it really should have a 12 in there. And then I would see the 12, and then I'd jump over to the 12, and I'd see a 13 there, and then I'd jump over to the 13, I'd see a -8 there, and that means 13 is our overall root. So that gave me a 13. But because of all of those little jumps that I made, I now know, for example, 16 points directly to 13. And for example, if there's like multiple steps along there too, they would also be able to be path compressed up to 13. Any questions on how I did that find set stuff real quick? I don't want to go too fast. So now that I've got these items, who is going to absorb whom? If we've got a choice between the set represented by 13 and the set represented by 3, who remains the supreme overall root? Who comes out on top? 13. Why did we pick 13? Yeah, it's heavier weight. Yeah, exactly. 8 is greater than 6. 13 is thus heavier than 3. I don't know anything about sumo, but maybe that means that 13 pushed 3 out of the ring somehow, but weight wins in this case. So what that means is we're going to do this thing where we're going to kind of just whoop, 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 0.3 directly at 13. And so now I've got some indices of the array I need to go in and update. So first off, I'm going to go in and I'm going to update these path compressions. The path compressions are technically happening within find set. Find set also happens to be called within union, But that's why we put the path compression there, because then we're improving upon our trees always as we go. And so what would then happen, right, is we would sort of like redirect this pointer. And the way that I'm going to do that is instead of storing 0 at index 2, I'm just going to update that to point directly at 3. And then also over here, I'm going to change 16 to point directly at 13. And so I can just change this 12 to be a 13 as well. So that's sort of my path compressions there. Now that I've got these slightly compressed trees, all I need to do in order to accomplish this union is I know that I want to change 3's parent, which is right now indicated by -6. I want to change that to be 13. So like, you know, sort of like one thing is the path compression. 2 things is updating this pointer. You know, maybe that's the 2. But then the third thing is I have to update this weight. So now, whoops. This is 8 plus 6, which I hope is 14, if I can do math sometimes. Yep. Great. And then it means I just need to update this here. And that's sort of like my third step there. Questions on how we accomplish unioning or path compression by using the array as the representation? Yes. So the point of path compression is in the future, if I wanted to find the overall root of 16, for example, I'd have one level less to travel. Also, this helps all of 16's children. Like, I'm just sort of making the trees a little bit squatter, and the squatter the trees are, the less iterations I have to do to find a set necessarily, which means the more optimal the runtime. And so in the ideal state, what we would end up with is just like trees with one level, something like that, right? And then we would never really have, like, our log n runtime would just turn into essentially a constant runtime to find anyone's overall root kind of thing. So that's like the directionality we're headed, but technically the runtime is based on log n to find set, and that log n is based on the height of the tree. So we're doing our best to compress the height of the tree and the length of any path from a given child up to its overall root parent. So it's not going to help us on the call that we're doing the compressions on, but it will help us on future calls. So this is an optimization for future functionality. So the more we use this disjoint set, the more efficient it gets, which is kind of exciting. Yeah.
Why do we compress before we perform the union?
Yeah, so we're going to compress before so that when we kind of move everything over, we like moved over the compressed tree, right? So that's nice in that case. And then also too, it's because we're going to put the compressions inside the find set functionality, so that anytime you call find set, we're just going to run that operation, because that's where we're doing that logic to like start at the child and then jump up kind of thing. And so just like the pseudocode for union is you have to find set on both of the two things, so you know whether or not they should be union together. Great question. Yeah. You know, you're just going to have to deal with the path compression just once inside of the find set call. So you only have to do it once per each of the two things that you're unioning. So I think, let's see if I have some useful pseudocode back into our slides. Here we go. Great. There we did some union. Great. There we go. So on and so far. Okay, apparently I don't have helpful code. How dare I? But yeah, for context, like union, the pseudocode of union is find set of the first item, find set of the second item, check if those two results are the same. If they're not the same, then pick whoever is bigger and make the smaller one point to the bigger one. So because we only call find set twice in the pseudocode, that's where we perform the path compression, just inside the method find set. Any other questions about these examples? Cool. Wait, did I forget? I straight up might have forgotten a why. Should we trust it? Okay. I just realized that I forgot an administrivia slide. So I just wanted to pause here. Reminder that May 22nd is the date for the checkpoint. You need, I think, 15 out of 30 points to get the 3 extra credit points added on to your total extra credit points. This is just our way to incentivize you getting started early. Please know that Project 4 is a sizable project. There are 3 separate pieces. There are 3 weeks for you to do it in. The intention is that this is the kind of project that you could talk about in your interviews and like put on your resume. So we made it hefty and with many imageries, GUIs, applications, things like that. Also, I think it's fun. Is that shameful? I don't know. I regret saying that because inevitably somebody will have a bad time with this and they'll be like, Casey, how dare you have described this as fun? And I'm like, I know. I'm sorry. Exercise 4 is due, exercise 5 is due this week. Your final exercise 6 will go out on Friday. We are still working on your midterm grades, and figuring out exactly what the format of the final exam will be. And as soon as we have updates on that, I will update you. Anyone have any administrative questions? Cool. Okay. As you can tell, today is our last day with graphs, y'all. All we're doing today is wrapping up some final conversations. We're going to do a graph modeling problem. And then on Wednesday, we're going to officially transition to our sorting conversation. So we're going to talk about sorting algorithms for a few days. Then we're going to talk about dynamic programming for a day or so, which is another algorithm optimization method. And then we're going to talk about the PNP problem, which is, I think, very interesting. And then we're going to wrap it up with a final conversation about memory, that sort of non-theoretical thing that I kept hinting at. And that's it for the rest of the quarter, which is bananas. But please, this is, like I said, our last unit, or our last day together on graphs. So if you have any other graph questions, now's the time. So far, we've been talking about disjoint sets for the last 2.5 days. Disjoint sets is how you're going to implement Kruskal's. So P4 says build a disjoint set, use the disjoint set to implement Kruskal's, and then the final portion of Project 4 is implementing Dijkstra's. So we have a bunch of this sort of Dijkstra pseudocode. You can directly copy and paste the pseudocode into your code if it makes sense to you and just go line by line and transform it. But I just wanted to make sure that we sort of chatted about things to make sure that we feel comfortable with what all of the pieces are. So on this, right, we have a few different collections. And this is the thing that's also a little funny, and I do want students to get this practice, is that we're sort of transitioning away from the world where objects are these pure nodes with fields and everything's encapsulated in that thing. That does sound nice sort of organizationally, but you'll actually find that you improve your runtimes by leveraging hash maps and sort of supplemental structures like this. So often you'll find that you do need to keep, for example, a set to know which vertices that you've traveled to. And then instead of, say, adding fields to the nodes, we're just going to create a map that tells you which of the edges you are traveling along, the back pointers, if you will. Sometimes we call these the edge 2. And then we're also going to have a separate map that's going to store from vertex to the distance that it will require to travel to that vertex. So you need three separate collections here to run Dijkstra's. A set to know which vertices have I already processed. This in the little table for Dijkstra's, you can think of that as sort of there's usually a column that says processed, ? And then you put a check mark, or you put a Y, say yes. That's what this data structure is representing. Then you usually have an edge 2 column where you would put the name of the vertex that you come from when you finally select, yes, this is the path to this item. Those are sometimes called the back pointers. That's what that's referring to. And then the distance 2, initially everything starts out as infinity. And then maybe you start to update those infinities to smaller things. And then when you're finally yes, this is the path I'm journeying, you're going to finalize that distance and sort of mark it. And we're going to put those things in maps so that you get that constant time lookup, constant time set, just vertex to information kind of thing, instead of, say, having to go jump into that object and pull it out as a field and et cetera, et cetera. This is actually going to be runtime much faster to do those types of things. So then this line, initialize distance 2 with all nodes mapped to infinity, right? That's this map. Just going to go in, dump in entries for every single item, and then set them all to infinity, except for the start node, you're going to set that to 0. So remember, Dijkstra's does need to take in a vertex to start. And Dijkstra's is always calculating the shortest distance from that vertex to every other vertex. Shortest path tree. Not about connectivity, that's the MST, shortest path tree. Then we're going to loop while this set does not have everybody in it. So while there are still unknown vertices left to process, then we will look at the closest unknown vertex. We look at our sort of like set of immediate neighbors. We add them to our known set. And then for each edge that sort of like connects us, we loop over each one and we check, hey, like if we calculate the current distance from plus the weight of that edge, is that new total distance here, the new dist, is that smaller than the old dist? And the first time we hit this, that's always going to be yes, because initially old dist will always be infinity, right? And that's why we set that into infinity. If it also helps, you could set this to max int. That's essentially the equivalent of infinity in the implementation. And that's so that the first time we ever see a vertex, we do map that distance, but it still gives us this opportunity that as we continue to move through the graph, if we discover a newer, shorter way to get to something, it will go in and it will update that distance. So maybe your distance 2 starts as infinity and then goes to some number and that's it, that's the only thing. Or maybe it goes from infinity to some number to some smaller number. But that's why Dijkstra's handles that. And then, you know, if this is a new distance, then you update the distance and you update the edge pointer. Any questions about this pseudocode and how you might implement it? Because that's what we're asking you to do. Yeah.
So it's like edge 2, are the values like sets all the nodes that coming to the from?
So edge 2 is going to be a map from vertices to vertices. So you can see what you're going to put in is like, hi, my vertex that I'm talking about, and then its value will be the edge, like, or the vertex from which you came. So in this example, I just want a graph. In this example, like, let's say here we go. We updated A to, why doesn't this one even have a name? Let's call this the unknown name. Like A's map would store in distance to a 6. And so you would have a key being A and the value being 6. That's the distance to map. In the back pointer map, you have A as the key, and then you would have whatever the name of this node is as the value, meaning like, hey, that's the vertex I came from in order to get to that sort of back pointer direction. Yeah. So you're only going to select one way in. Yeah. So that's exactly why it's going to be that 1-to-1 ratio. And you're right, there might be multiple ways in, but you're not going to like, you're always going to only store one value, and that value will be the vertex that comes immediately before this one in what we think of as the current shortest distance to get there. So if we find a new way that's like shorter, then we would go and we'd update the distance, and we would have to update the edge 2 to being like, no, instead of coming down that path, you're going to come down this path instead, kind of thing. Yeah. Any other questions? Cool. Okay. Okay. These things we've all seen before. Yes. Thank you, Pas Casey. That is a good thing to remind people of. There is this line here, let U be the closest unknown vertex. So you might have a few immediate neighbors, right? But we specifically want to select the one that is connected by the smallest edge weight. So it has to be, and this is directed, right? So it has to be an edge where I'm starting from where, let's see, V is, and I'm looking at all of my neighbors, and those are all sort of like outgoing edges from V, and I'm going to look at all of the outgoing edges from V and pick which one is the shortest. You could like loop over all of them and maybe put in like a couple if statements to do a bunch of like math.min comparisons or things like that. Or you could just dump all of the edges into a min priority queue and just remove min to find the smallest item. It's almost like all of the data structures we've been teaching you are slowly starting to come together, because once upon a time, this project all built on everything. So you can use a minimum priority queue right here in order to shake out who is my next closest neighbor. And remember that the way that we're representing this graph is with an adjacency list. So the way that you're going to do that is you've got this sort of collection from every vertex to a collection of its next door neighbors. So in order to do this, all you got to do is like go grab the collection of neighbors from the adjacency list, loop over the collection of neighbors, dump it into the min priority queue, and then remove min, and that's your next closest neighbor. And then you kind of move through this process where you add that individual neighbor to the known set, you see if you need to update the distance, so on and so forth. So you're only adding one item to the known set at every step, though you may be considering multiple immediate neighbors. Any questions about that? No? Cool. Okay. Yeah, here is some more detail. You can see there, we sort of added in this like minimum priority queue, so you can see how that pseudocode transforms. Also, too, you can see how maybe we use change priority in order to update those things. We literally had you implement change priority specifically so you could use the priority queue in this context. We used to make you use your own code, but that was a disaster. So now we just replaced your code with our code, which is why in Project 3's turn-in, you saw the chained hash map code. That was like our chained hash map code, because that's from quarters gone by. We should really take that out of the grade scope. But I will let you read through these things. This is the runtime of all of this. I used to spend a huge amount of time proving to you that this is the runtime, but here's what I'll tell you for Dijkstra's. The runtime is E log V. Essentially, yeah, you're going to touch every single edge, and for every edge, you're going to make some sort of decision about the pathways through it, so you can get that log V runtime. Yeah. Oh, it should be E. There it is. It should be E log V plus V log V, actually. There's your final. Yeah. You can tell this would have spent an entire day of lecture, but there you go. This is sort of considered the canonical runtime of Dijkstra's. Cool. Great. Yeah. I'll let you read those. I'll let you read these slides. I think, like, if you're talking about this in terms of interviewing or having conversations, I would be very shocked if anybody in particular wants you to prove these types of things. But you could look through how all of these runtimes build up, right? And hopefully we've started, like, for example, we see a log V of removing min from the priority queue, right? And then here we've got for each edge, so there's a factor of E. And so I do think it might be valuable to go in and look at the sort of sub runtimes in here, like log V to change the priority within a heap, log V to add something into the heap, those kinds of things, and you get that sort of E log V in order to just loop over items. But then we've got all of this initialization that we've got to do up here, where we create maps for each of these vertices, and we've got the priority queue, so that's where we get that V log V plus E log V runtime. Okay, I'm going to take the last bit of class and I'm going to talk about what I call a graph modeling style question. It is very, very likely you will have a style of question like this on your final exam. Also, I think these styles of questions are very similar to interview questions. And also, I used to get like a little too extra with writing midterm questions. And I thought I was just being so cute and funny. And a lot of people feel that way about interviews. So though I will admit that it was annoying when I did it, people definitely do it when it comes to interview questions. So let's talk about them so you are prepared to answer these questions on the final exam and possibly in interviews. So when I say a graph modeling problem, we've been learning all these things about graphs, we've been learning all these algorithms. The goal is to give you some type of real world scenario and then go from the real world scenario to some type of graph model. What are your vertices? What are your edges? What are your weights? Is it directed? How are you going to represent the specific scenario and all the relationships that you need to represent in this sort of logical, symbolic way of a graph so that eventually we can say run BFS or DFS to check connectivity, or we can run Dijkstras to find the shortest path, or we can run Kruskalls to find the minimum spanning tree. That's why we're trying to get things into this sort of like representation. And so usually you start with your scenario and then you got to pick what are your vertices, what are your edges, directed, undirected, weighted, cyclic, all that stuff. And then you just kind of figure out like what understanding can I draw of the scenario based on the algorithm. So we've got, do we just need to visit every single node? Maybe we need to like do some calculation or check what's in the set, BFS or DFS. If I just need to see if two things are connected from any point on the graph to any other point on the graph, that's BFS or DFS. That also checks connectivity. Remember, these things will just run through every node that is connected. It does that sort of web crawly thing, right? So that'll tell us how to just traverse over a graph. It'll also tell us if two things are connected. If you don't have weights, but you want to get the shortest path, you run BFS. If you do have weights, then you run Dijkstras. And then if you want to check connectivity and you want to minimize the total summation of the edge weights, that's when you run Prims or Kruskalls. You'll probably be a little bit more familiar with Kruskalls. And that's how you get your answer. So let's do an example. Okay, this is a real midterm question. I did not make these slides either. One of my TAs made these slides a while ago, which I think is funny because I thought I was being so cute with this midterm question. Okay, here's how it works. Okay, imagine you are an American high school student and you have a very important note to pass to your crush. But the two of you do not share a class, so you need to rely on a chain of friends to pass the note along for you. And a note can only be passed from one student to the other if they are in the same class. So when two students have the same teacher during the same class period. So for example, you can see your period 1 is with Mr. Smith, so you are in class with Anika. That's how that kind of works. Unfortunately, the school administration they're not romantics, and they think passing notes is against the rules, and they are going to intercept these notes. So a teacher will take it and destroy it, and your heart will be crushed, because that is the American school system. And so you need to figure out if there is a sequence of handoffs to enable you to get your note from you to your crush. And here is a little sort of chart to determine who's in what period with whom. How might we model this as a graph? Let's start there. So here's just a scenario. Before I maybe ask any questions, does anyone have any clarifying questions about the scenario? Oh, yeah? Yes? Great question. Yeah, like, does this have to be, so right now it doesn't list that it has to happen in one day, but for example, if your note hasn't gotten to somebody by period 4, let's just assume fabulous community behavior, and then that person, whoever it lands with period 4, will keep it with them in their note bag and then maybe come back in period 1 the next day or something. Maybe they pass it along. Then what would we suggest to make the vertices of this graph if we were going to make this into a graph? Any suggestions? Anyone want to raise their hand, give me a guess? Yeah. The people. I agree. So since we're trying to do this kind of idea of like, okay, like I have a note and I want to get my note from me to another destination. And if I am the source and my destination is my crush, that sort of ends up with like the people as like the vertex-centric things. And whenever I think about what goes into the vertex, I think, what is the core piece of data? That's usually what becomes the vertex, and the relationships between the data is what becomes the edges. So, for example, in the social media situation, profiles are vertices and follow or friend connections are the edges, because that's how that would connect to profiles. If we're going to make the students the vertices here, what would we make the edges? Any suggestions? Yeah. The class, absolutely. The class, especially a shared class specifically. So for example, I would maybe make myself, a vertex here, and then I would add an edge to Anika, and maybe I would label that edge like period 1 or Smith or something like that, or maybe I'd put both of those labels on there. And that would mark that I have a connection to Anika. We are in the same period 1 class. Any questions about that sort of representation? Yeah.
You can also label it period 4 because you also share the same period 4 as well.
Ooh, good question. So I love that you looked in this table, and you can see Anika and I also share period 4. So what do you think? Should we put period 1 and period 4 on the same edge? Or how would we represent that Anika and I have 2 classes together? Any ideas? Yeah. You could have just 2 edges. Absolutely. So probably what I would do as well is I would have one edge between me and Anika that's labeled period 1, Mr. Smith, and then a separate edge that would be labeled period 4, Mr. Brown. You could probably refer to that as a parallel edge because they're 2 edges with the same, connecting vertices, but they represent different pieces of information. Yeah? Great example. Other thoughts on just the modeling of this? Yes?
Well, it kind of goes back to the idea of like period 1 people can pass period 2 people, and period 2 people cannot pass period 1.
So, for example, if I share period 1 with Anika, then right now, and if you see, that's kind of the only person I share period 1 with. So the only person I could give my note to initially is Anika. Let's say I missed that or something, and then I'm like, oh, I got nervous, I didn't want to give it to Anika, I don't know, and I show up in period 2. I noticed that in period 2, I share that with Bao. So maybe in period 2, I'd get up my courage and I would give my note to Bao. And then my note would be in Bao's hand, and then maybe in period 3, Bao would be like, okay, who do I share it with? Oh, apparently Bao shares period 3 with Anika, and maybe then Bao would give it to Anika. And then in period 4, Anika shares it with me, and somehow it would come back to me with a bunch of ridiculous sayings on it, and I would be embarrassed. I don't know. High school is cruel. But the idea is that we're sort of only transferring ownership of the note in a shared class. Yeah? Questions? Yeah. Yes, agreed. So, for example, if me, Anika, and Bao all had Mr. Smith first period, I could choose whether I want to give it to Anika or Bao. There's only one note, so you got to pick one. It's like a baton situation. I only wrote one note. Keep the evidence limited. Will you go to prom? Yes, no, maybe. Sure. So let's see. It's got to go through hand. So let's say I passed it to Anika in period 1. And then in period 2, let's see, Anika shares period 2 with Dan. They both have Mr. Lee. So Anika could give it to Dan. Or Anika could wait. Maybe she doesn't trust Dan. I don't know. And then Anika has period 3 with Bao. And Bao is apparently much more trustworthy. So Anika hands it off to Bao in that period. So I can the note can change hands when I have a shared class with one of my friends in this list. Yeah, question?
Wouldn't this be better if we just map these out as different graphs for each period?
So how would you get from period to period if they were different graphs for each period? So then I think the question is, here's, for example, a drawing of what it might look like. Because the question is, I want to see how the note gets from my hands in period 1 to my crush's hands at some later period. So I want the graph to cover multiple periods. And the other reason I use this example too is, notice I can store whatever I want in the edges. So in these cases, I stored both the period number and the name of the instructor. Whoopsies. So here's a drawing of what it might look like based on that picture, and here's what the adjacency list might look like as well. So you can kind of see those things all sort of shaken out. I will show you the last bits of this just in the interest of time, but I'll let you sort of read these things. One other thing I did is, as part of this question, once you have the graph, I then asked, when's the soonest your note can get to your crush? And so if we assume that the period numbers come in relation to what time they are during the day, i.e. period 1 is the earliest in the morning and period 2 is the second earliest in the morning, et cetera, we can run Dijkstra's if we use the period numbers as weights to find the shortest path to get from me to my crush by the end of the day. I might end up hitting my like rollover period thing, and I will fully admit, like, we kind of took that like rollover part out of the midterm because we thought that was cruel. But if I use the period numbers, that could help me get that shortest path, figure out what's the earliest in the day my note could get to my crush. One other piece I'll show you too. So this was optimizing for time. Another way to optimize is for risk. Remember I told you that, like, if a teacher sees it, they're going to take it? Well, what if we knew how likely it is that a teacher takes notes? So maybe we keep an eye. And there are certain teachers, Mr. Brown, who are particularly effective at intercepting notes. And so in that case, then what we could do is, here I've changed this. I've got the same graph with the same relationships, but the weight that I've put is the number of notes intercepted by each teacher, with the assumption being, hey, if a teacher intercepts more notes, they're more likely to continue to intercept notes. And so again, I can just run Dijkstra's, but use the weight of how many notes the teachers have intercepted to try and find the path through to my crush, only swapping hands in periods with the least amount of notes intercepted. So that's an example of a graph modeling problem. I just wanted to talk through it with y'all. I'll let you read. I think I made these things pretty text heady if you want to read them. Thanks so much, everyone. That sort of concludes our graph unit. Come back on Wednesday, and we're going to talk about sorting algorithms. Yay!